Hello, Professor Udin and teacher assistants. Welcome to our team presentation number 2. Our project is categorizing the content of a GitHub README files. Our team consists of Bhavya Gupta, Coyote Ah, as well as myself, Michael Lee. So now let us start off the presentation with the data collection breakdown. Now, as you can see from the research paper, the classifier is divided into 8 categories, where category number 1 is what, category 2 is why, category 3 is how, category 4 is when, category 5 is who, category 6 is references, category 7 is contributions, and category 8 is other. Now, it was mentioned in the research paper as to how many sections it was counted for each category during their manual annotation. As part of this project, we have also added a couple of files that make up a little bit over 1,000 sections from which we put our manual annotations on. And these sections that we added have the labeled categorized, as you can see from the column under section count for new files. We then thus tabulated the section count for the original files plus the section count for the new files in our total column, as you can see from the rightmost column in front of you. Note that the section count for new files are not finalized yet and may subject to changes in the final report.
In this section of the presentation, I will be discussing about the quality of our data labeling. I'll be talking about the categories used when we are classifying the data. I will also talk about the agreement between the data labelers and how we were able to resolve the few disagreements we had during the manual annotation process. Now I would like to discuss about the categories used in classifying each README file sections. Various code were given to different sections of each README file. For example, code 1 was chosen for any section that is discussing about the introduction or talking about the project background. Code number 2 is about any advantages of the project, or when the project is being compared with another related work. Code 3 is mainly about instructions of getting started with the project, how to start, how to run, how to install, how to update, how to configure, how to set up, languages, demo, errors and bugs. Code 4 is talking about the timeline of a project, like the status, the versions, project plan, and roadmap. Code 5 is about the people that constituted the project team, the community, mailing list, contacts, acknowledgement, license, and code of conduct. Code 6 is talking about the references, the documentation, how to get support, feedback, how to search for more information, and also about related projects. Code number 7 is about different guidelines for contributing to the project. And in the case where we are not able to fit in any of these sections into this code, then we give it code number 8, which is tagged under other, as the case may be. Agreement between the data labelers. 2 metrics were used during this process of comparing the manual annotation. Number 1, we used the percentage agreement metric, and we also used Kappa to determine the agreement between 2 data labelers. The results show that both metrics were very close to each other. They actually return a metric of over 90%. a table is showing on this slide that shows the result of percentage agreement, which is also known as inter-written agreement IRR, with the results of 95%. This table is displaying the result of Cohen-Kappa analysis 2 with 1089 README file sections between the two data labelers. As you can see, the Cohen-Kappa returns a measure of agreement of 0.941, which translates to 94.1%. One of the advantages is that a Cohen-Kappa has over a simple percentage agreement is that it takes care of an agreement by chance. So there is an elimination of agreement by chance, which makes the result to be more valid. So we have this table for the different README file section code for each labelers, and it displays the count of each code, the expected count, and at the end of the day, we're able to get a very good score of around 94.1%, which is very close to the earlier result we got using a simple percentage agreement tool. Since we still had a few areas of disagreement during the manual annotation process of the README file, we came out with a way of addressing those issues. What we did was that we went back to each of the area of disagreement and re-examined it, and finally came up with a final code for the particular sessions. Some of the most common areas of disagreement are in the title sections and some other sections that are so ambiguous. For instance, under some question and answer section, one labeler categorized a particular section as 1 and 3, while the other labeler categorizes it as 3. This example is actually taken from a particular README file from a WordPress skeleton project. The main reason why the first labeler categorized this section of the README file as 1 and 3 is because the section was giving an explanation of the project, which fall under category 1. And at the same time, there is also some instruction being given, which made the labeler to give it another code of 3, which fall under what. Meanwhile, the second labeler was convinced that the section was only giving an explanation about the project, and the labeler gave it a code of 3. So when we look at all this, we decided to have a second look on those areas that there were some differences, and we came up with a particular code that we felt would be the best to categorize it.
We have already talked about data labeling in the previous slides. In this slide, let's go a step back and see how we collected the data in the first place. The original research paper had 435 README files containing about 4,922 sections. For this project, we need to have 1,000 new sections for manual annotation. So we wrote a script that we call readme-downloader.py. As the name suggests, it downloads readme.md files from GitHub using GitHub API. All these files, the readme.md files that are downloaded, are randomly chosen, but it is made sure that these files are unique. Also, the files downloaded belong only to the software development repository and have size greater than 2 KB. Now, let's have a look at our code that we have written. So this is our code, all of this. Now, we won't make this presentation boring by going through all the code, but we will show a few important details. The first one is this file. As you see, it's available here. So this is basically a GitHub personal access token. We need a personal access token from GitHub, as GitHub only allows 60 requests per hour if we don't use it. If we are using it, we get 5,000 requests per hour so that we can download large number of README files. The second thing is this README count variable. So this is basically tell us the number of files that we want to download. For the demonstration, let's take a smaller number like 3. And the last detail that we want to show is this file. So this is the original file, from the research project, from the research paper. So our script reads this URL and while fetching the README files, it basically makes sure that any README file that we are fetching does not belong to any of these repositories, to make sure what we are downloading is unique. Now let's run our script and see what we get. So as you see, it has created this file and this folder. So the script has finished running. This is the logs generated. Let's have a quick glance. Okay. And this is basically an index of the files that have been downloaded, and these are the actual files. So if we take a look, let's say, let's have a look at this one. So this is basically a foreign language file. So we are filtering the foreign language files manually by ourselves. The script doesn't do it. Let's check this file. Yeah, so this is in English and it's a very nice file. Similarly, let's take this one. Yeah, this one as well. So this is how we collected our data. So as of now, we are using about 89 README files that we have downloaded using our code. Pre-processing of data. The pre-processing is basically processing of raw data before that data is fed to the machine learning model. The pre-processing can involve filtering of noise, tokenization, or stop word removal. Let's see what pre-processing we are doing in our README classifier project. The first is content abstraction. It basically abstracts contents to their types. So if our README file contains any of these types, they are basically replaced with these strings. So if there's any code snippets present in the README file, they all are replaced with this one string. Same goes for numbers, images, and hyperlinks. This is done because we are more interested towards knowing whether these types exist in our README sections or not, rather than the actual content of these types. So let us see this content abstraction to understand it in more detail. So this is our README file, the source code of our README file. Let's turn the Markdown on so that we can see it in proper HTML format. So we have created this README file on our own rather than taking from GitHub, because we wanted to include every type of content that is getting abstracted by during the pre-processing. So for example, it contains numbers, inline links, normal hyperlinks, images, code snippets, inline code, and mail to links. So let us see what happens when we pre-process this README file. The output of this will be reflected here. So right now there's no file, and in the database. So this is a temporary database where information is stored for intermediary processing. Let's run the script. Okay. So let's first check the final README file. So as you can see, the numbers, the hyperlinks, all are replaced with their abstract strings. The same goes for images, code segments, and mail to links as well. The inline code are basically remain untouched because it may contain data that might be useful for the machine learning model. And these inline links are basically removed. So what remains is just plain text. Okay, now let's check out the database. So everything that we see in the README file here is basically here as well. So the URL, this is basically a dummy URL. The name of the file, the heading markdown, what happens after that is being abstracted, the actual text, the abstracted because there's nothing to abstract in the heading, that's why it's like this. And the heading levels basically determined by a number of hashes. If we check out the content file, so here we can see all the abstracted data is how it is stored. So for example, let's test this one, number 4. So section number 4. So below, so this basically this all content. So originally it was this content, all of this. Now this got converted to this after the content abstraction, and this is exactly how it is stored in the database. So after content abstraction, tokenization and stop word removal is done as part of pre-processing of data. So both of these, tokenization and stop word removal, is done using a scikit-learn instead of NLTK. So as you can see, here is the code segment that shows how tokenization and stop word removal is handled when we instantiate TF-IDF vectorizer. We'll discuss more about TF-IDF in later slides. The last part of pre-processing of data is encoding. As we have mentioned before, README sections are classified based on what they answer about the project. These classifications are numbered from 1 to 8 during manual classifications and predictions from the model. But as part of pre-processing, we use multi-label binarizer to encode these numbers into a sparse matrix before feeding these to the model. Here is a quick glance at a table that describes the section classifications. Now, let's see how multi-label binarizer works. So you can, if you see here, you can't see section 2 because it is merged with section 1, basically. And this dash basically means exclusion. So in the sample README file that we have seen before, the output that we get after multi-label binarizer is this sparse matrix. So if I pull up my database, as you see, we have labeled the first heading as the first section as 3. So in the output of the multi-label binarizer, so we see 1 in this location, in this index. The same goes for all of these. So these two ones represent 1 and 3. So if I check third one, so this is 1 and 3. Similarly for 8 is for, let's check for this one, 8 at the 6th row. So here is 1 representing 8. So this is how this matrix is going to be fed into the model. Let us now talk about feature extraction. All the pre-processing that we have done on our data aids us in extracting the features. We are extracting two kinds of features from our pre-processed data: statistical features and heuristic features. Statistical features tell us about the word statistics. We use both content and the headings to generate these statistical features. To generate these statistical features, we use TF-IDF. We have already seen how TF-IDF vectorizer is instantiated in one of the previous slides. So basically, TF in TF-IDF means term frequency. It means the number of times a word appears in each section. IDF means inverse document frequency. So the IDF of a word is reciprocal of the number of sections in which that word appears. So when we instantiate the TF-IDF vectorizer, it is basically the product of these two, TF and IDF. Let us now see how this TF-IDF works. The list of words that we see here is basically coming from the abstracted README file after tokenization and stop word removal. So we initially had this README file. As we have seen before, it got abstracted and we got this. After the abstraction, this file got tokenized and got stop word removed, and what we have is finally this list of words. What we see here is the TF-IDF matrix. So as the column matrix, we have all the words from the list, and as the row index, we have all the section numbers. The values that we see are the TF-IDF values. So these TF-IDF values are already normalized. So if we want to see the relative meaning of each of these values, let us compare it with what we have in the README file. So for example, if we see, we have non-zero values for this code section only for one particular section, section number 4, which is the second last section. And for all the other, it is 0. So let us see why. If we see in our README file, we can see the code section only in the 4th section. Basically, we should check this one. So this particular string is present only in this particular section. That's why it is non-zero here and 0 elsewhere. Similarly, if we see, let's say this VCS, if we search for the word VCS in our README file, we must see this word only in sections, only in the 2nd section and the 4th section. Let us see. Okay, so as we can see, we can find the word VCS, version control system, only in the 2nd section and the 4th section. It is not present elsewhere. So this is just the index. So that is why we have only non-zero VCS for these two and 0 elsewhere. So this TF-IDF matrix is what basically is fed to the model. Finally, let's talk about the heuristic features. We are extracting a total of 55 binary heuristic features from the README content and the headings. So these 55 binary heuristic features are categorized into 4 types: linguistic patterns, single word non-English heading, repository name, and non-ASCII content text. So the information about all these heuristic features, the functions, and their description is in this Excel. Let's come back to this Excel real quick, but first, let us see how these heuristic features look like. So what we have here is the transpose of the heuristic data frame. So as you can see, these 1 to 5 are again these sections, and these are the heuristic features. So most of the values are 0 based upon the sample README file that we have fed, but some values are 1. Let us check why these values are 1. Let us first check about this one, where each section has this heuristic feature as 1. We will use our Excel to see what this means and why these are 1s. So we can double click to open this. Okay. As we can see, this heuristic feature that we are talking about is based on is actually one when the content comprises entirely of the ASCII characters. As our README file is all about ASCII characters, so all of these sections are basically one. Now let's see what why this one is one, and let's see what this feature means. So as we can see, this feature means our section contains you can. So this would mean our second last section would contain you can string. Let us search here. Yeah, so you can string is present only in the second last section, and that is why it is one here. Let's do one final test for this feature. Okay, the third one. So this feature is one only when our README content contains the abstract section code. Basically, it contains code snippets. So obviously, as we have seen before, only the second last section again contains the code section, and that is why our heuristic feature is one for this particular section and zero for every other section. So again, this data frame, this matrix of heuristic features is also fed to the model.
So now let us talk about our machine learning model and our overall machine learning pipeline. So first, we will have the README files as well as our manual input annotations as the input for our pipeline. We will then use that data and input it into an abstraction system as mentioned before, as well as extracting the features from the data input through the statistical, like the TD-IDF, as well as the heuristic feature extraction as discussed before. We will then use this feature matrix and come up with a fitting model method in which we will then validate at the end to see whether or not we can improve the performance on the model itself. So now, as mentioned before, the X matrix, which is the matrix of features, will be defined by the TD-IDF as well as the heuristic feature extraction. Now, for the target vector, we will use the section labeling that we did manually, as well as the ones that are defined by the authors from the research paper itself. Now, as for the model, we will test out the performance of the original models that were experimented by the author, which are the random forest classifier, the linear SVC, the Gaussian naive Bayes, the logistic regression, as well as the k-neighbors classifier. In addition to that, we will also explore additional models that were not experimented before, which are the Bayesian classifier, the extra trees classifier, the decision tree classifier, the ADA boost classifier, as well as the histogram gradient boosting classifier. Now, the data will be split where 25% is used for training and the 75% is for validating the model using a 10-fold cross-validation. The score will then be calculated in terms of its overall performance, and from then on, we can then evaluate and optimize the model as part of this project, such as exploring the tweaking of hyperparameters, etc. And this concludes our presentation too. Thank you for listening, and see you in our next presentation.